G'day Bifrosters. The time has come. We're going to make our very first custom noise today. So today we're going to do Worley noise, which is also known as cell noise, or sometimes Voronoi noise. And it's a little bit different to what we've been doing before. What we've been doing before is noise that's based on a bunch of mathematical equations done to points in space. Now, Worley noise is still a bunch of mathematical equations done to points in space. It's just not done to the points that you bring in. Rather than pull up Wikipedia and dazzle you with all of the edits that other people have made on Wikipedia about Worley noise, about cell noise, what I thought we'd do is we'd just build it and see how it goes. So, to do that, and to do that in a way where we can see what's going on, what we're going to do is we're going to start just a new compound down here. And we're going to call this compound Proto-Worley. There we go. So the aim today is to get the basic Worley noise up and running. To do that, what we need to do is, instead of just taking the points in space that we have and using them as we do, we need to generate some more points. So we have a decision to make. How do we want to generate those points? Do we want to scatter them on a surface? Do we just want to go ahead and make a whole bunch of points in a sphere and raycast them to a surface? Let's have a look at what we're working with. So we'll get the geo into our compound. And the reason I'm setting up a compound now is so that we don't need to worry so much about anything that's going on out here. So this output, that kind of thing. Because, I mean, even though we do have stuff in the viewport, because we just want to work on Worley right now. So let's get this guy, and what we'll do is just throw this into a terminal for now. Terminal, there we are. So this is our input. Now there's a couple of quick changes I've made before we get started. I have 4 different things coming in here. I have a sphere and a plane, both created inside Bifrost. I have our friend the horse over here, and I have a platonic sphere over here, and I've just put them into a switch node, which is a node I've built which allows you to switch. So what I'm going to do is switch to the platonic sphere, or the icososphere. It's a platonic solid with lots and lots of divisions in it, and it's all triangles. Okay, fine. So we'll work on this, but we are going to have the ability to just like change it and see what it looks like on our horse, or see what it looks like on a plane. So that's just a handy thing that I've put in. It's not part of the noise tutorial at all, but it's just something that allows us to jump between inputs really, really quickly. So let's go back to our heavy icosphere, jump back into our noise, and jump back into our Proto-Worley, which is where we're working right now. Because of the way Worley noise works, because it's essentially this, if I take this and I scatter some points on it. And this is just a quick node I made up that uses sample locations to randomly scatter points on the positions of whatever you plug into it. Get a point display going on. Get a point display going on. We'll turn that on. Some black points will turn up. There's rather a lot of them right now, because scatter on object is for some reason set to 6,000. So let's go to 600, and we'll give this some kind of color, sort of a lightish blue. It's quite nice, isn't it? I quite like it. Spheres will do. The size is fine. This is just a look at. So the way Worley noise works is needs to find the distance of every point on our icosphere to one of these points. And what it does there is it basically either pushes in along the normals or pulls out along the normals these points based on how close they are to the closest feature point. I'm going to call it feature points from now on, because that's what I call them all the time. So these blue ones are the feature points, and these ones in here are just the points. Let's make our lives a little easier. Oh, I don't know if that's easier. Maybe that's a bit easier. Yeah, so these points here are just the geometry points. So geometry points, feature points. All right, just a bit of lexicon to go on with. We need to find the distance from each of these geo points to the closest feature point. Now, this is just the beginning, and the aim today is just to get this working. What we will do afterwards is add a bunch of the functionality that we're adding with our noise node, things like frequency and amplitude. At the moment, what we're going to do is we're just going to get the Worley noise working before we do anything else. So the very first thing we need to do is we need to get the point positions. We need to get the point positions from our input, because we're going to be doing an awful lot of work on that. And we need our feature position. So let's put these two both into pass nodes, so we can give them a name and we can work with them and we can do all sorts of nice stuff and try and keep our lives a little tidy. So this is our feature points. So let's call this feature points. Feature points, like so. And this is our geo points. And we're going for the absolute basic, no frills, get this working Worley cellular VII noise, or whatever it's called. Keep our displays up there, because they're not really that important, but we need to have them in the file. So the very first thing I need to do is I need to find out which one of these points is closest per point. So I'm going to need to build an array that is the same size as the array that makes up the object, with the index of this point in it, so that every point, it has an array that you can refer to, that the point number, say the point number is 17, it's the 18th thing in the array. The 18th thing in our new array will be the index of whatever the closest point is. So we need to build that first, and the way we're going to build that is with a loop. Well, actually with two. Is we need to loop through every single one of our geo points. So I'm going to hook this up here. I'm going to delete this because right now it's only going to do it 10 times, and I need it to do it on every single one of these in parallel, because it's nice and fast. We'll jump inside and we'll just really quickly set the iteration target to there. We also need the feature points in here. Alright, so let's just name this so we can keep this straight in our heads. And you know, that goes for me as well, because I have built this before, but I built this before about 3 months ago, and I'm stumbling in the dark just a little bit. Inside here we have each geo point going round the loop as usual. And we need to actually loop through these inside of here, so it's a nested loop for each. We need another for each with no max iterations, which is what we didn't do. We need that geo point that we're working on. Yes, I know, and we need the feature point in there. So let's just unhook that, which is giving us problems at the moment, and hook that up. So now what we've got is we've got 2 points. So for every time through the loop on a geo point, it's now going to loop through every single feature point at the same time. All I want to find out inside this loop is the distance. I want to make an array of the distance from the geo point we're working on to all of the feature points. So to do that, we just need to subtract, like so. And we're going to subtract the feature point from the geo point. Then we are going to get the length. We're going to do a couple of quick bits of renaming. So distance vector and distance would be a good start there. And then we'll put this in here. This is what gets output. So all this does is it builds us an array. It builds us an array of the distances from every single geo point to all of the feature points. So the length of this array is the same as the length of the feature points. Remember that, it's important later. We're still inside the loop where we're looping around every geo point at the moment. So what I'm going to do is I'm going to take this out distance and I'm going to sort this array. I'm going to press tab first. Sort array. So this is going to put that array, the float array of distances, in order from smallest to largest. Yeah. And what we need is the smallest. Later on we're going to be able to control that, but for now we just need the smallest. So that's simply done by doing first an array like this. That will get us the one we want. But I'm not going to use that because I happen to know there's some functionality coming later on. So I'm going to get from array. So here I'm just going to make sure the index is 0. So this is getting the first in this array. And the first in this sorted array of distances is the closest feature point. Okay, so remember this is the distance from every single feature point to the point we're working on. So it goes through every single feature point inside here and returns an array of the distances to those feature points from the geo point we're working on right now. Therefore, if we sort the array and we get the first one, which will be the smallest one because the array sorts from smallest to largest, that will be the closest feature point to this particular geo point that we're working on. What I need is the index of that point. So to do that, I'm going to do a find an array. And of course Bifrost does that because because I've got bad habits or it just hates me. I want to find something in an array. What array do I want to find it in? Well, I want to find it in this distance array because before we sort it, this is just giving us the same order as the feature points array. And what I want to do is find something in the feature points array. I need this order basically. And what I'm trying to find is this value. And I want to make sure I'm starting at 0. So it's going to find in this big list of distances the one that matches the smallest, which gets me the index of the feature point. Because the array with the distances is in the same order as the feature points array itself. So this is going to return to me the index of the closest feature point to this geo point in that whole feature points array. And that's what I want. It's the first thing I want. Like this is the first thing I want. Closest feature point index. Hopefully that's not too confusing. This is probably the most confusing thing we're going to do because everything else we do from here is just distances. So now I have the closest feature point. What am I going to do with it? Okay, so now we've found the closest feature point to any given point and we've spat out a great big array of them. There they are. Now what this array will contain is the index of each feature point for every geo point. So the size of this array will be the same as the size of this array. The order of this array will also be the same as it will also be the order of this array. So what we can do now is we can get from this array, and we'll be able to get the feature point. So now this has created a new array with the same size as this one, containing the index of the closest point from here. So now this is a different size to this. It's the same size as that and the same size as this. This allows us to go, wow, this is turning into a lesson in arrays, isn't it? I mean, I suppose I should be practicing for my Hobbit reading, but you know. This allows us to get the distance by subtracting one from the other and then getting the length. And this will be the distance to the closest feature point for each geo point. Time to start doing something with it, basically. First thing I'm going to try and do with it is basically, we'll pull our terminal over. First I need to see if this has worked, because it may not have. But let's pop this out as color and see what we can do, if I can get the terminal to work with color. So we'll do a float to grayscale, which is a node I built that just takes an array of floats and turns them into black and white colors for us. And then in here we'll do a set geo property. Like this, we'll make that property color. And we'll drop the 4 grays into the data and see what happens. Nothing. This could be for several reasons. First among them is that my data is wrong. So let's have a look, and if we have to troubleshoot, we troubleshoot. Get the watch point up. Yeah, we've got data coming through, and it's between 0 and 2. Okay, that's a little big, I guess. Probably needs to be between 0 and 1, but we should still have seen something here. Which leads me to believe that it's the old I'm not having fun trying to output stuff in the terminal from Bifrost. What happens if we delete that? Hey. Let's check the length of the array. 94092. That's cool. We've got a get point position, so let's find the length of that array. This one here. Here's a think. 94092. That's so far so good. That's the same. We needed it to be the same size to make sure everything's working. Troubleshooting. Come on, hide that info because you're going to annoy me. So is this just a color thing, perhaps? Turn that off, and let's just, to avoid confusion for now, let's just make this quite a lot smaller. Yeah, much better. Turn on the diagnostic. There we go. So now you can see it's already working. Let's turn off and we'll turn off our points as well. Thank you. So you can see that we have now, that's a Worley noise. That's a cellular noise. It's not doing any distortion yet, but you can see it's broken everything up into cells based on the distance from each point. We've assigned a color to it. Because that color goes above 1, it seems a lot whiter. So let's real quick, let's fix that by coming out here and going for a set range. And if this is the first one of my videos you've watched, this is a node of mine. You can make it yourself really, really easily by using an array bounds and a change range. The array bounds goes into the from start from end, and the numbers that you choose go into to start and to end. And that's how set range works. We're going to set ours to 111.0.0.0, but this fourth one this is the alpha channel, we need to make sure both of those are 1. And let's plug that in. Give it a minute. There we go. So that's a little more accurate now. So we've still got very definite black dots, but we do have cellular noise. This is cellular noise. It's only in the color channel at the moment, but we have cellular noise. It's working. It's working nicely. And we did it with 2 loops. Basically, we played with the arrays until we got the right indices out that we needed, and off we went. There's a lot of things we need to do with this now to make it pretty and usable and enable us to do things like change the frequency or offset the points, and it's all completely separate from the other noise we did, and that's because we had to generate our own points, which we've done here. Right now we can change the frequency. So we can change it to half the amount, and you get the idea. So what I would really like to do is change the way that, these colors will become, black will become minus 0.5, white will become 0.5. They will become our distortions on the noise. So we can do a lot of our setup on the colors ourselves to get an idea of what's going to come on. So what I would like to do before anything else is put a F-curve on this. And evaluate F-curve on this, and to do that I'm going to put that on the lengths coming out, and to make sure I'm not doing anything weird, I'm just going to check the sizes of this. The minimum is 0.0029 and the maximum is 3.4. So I think what I'm going to do is I'm going to move my set range from where it is at the moment, because set range is a fairly versatile node. I'm going to just put it in here, and I'm going to change these numbers to 0 and 1. So I might need a new set range to get it to pick up. No, it's not as versatile as I thought it was. Don't tell anybody. I'll get it to pick up the float. Yep. Oh, there we go, and we'll change that to 0 and 1 over here. So our distances are being remapped to 0 and 1. You can see the colors are just done the same. This is just a lot easier to work with an F-curve. I don't have to go through and manually set the highs and lows in the F-curve and stuff. So we'll just remove that watch point and we'll eval F-curve, which will break because it goes into the wrong plug, and I'll plug it into the right plug and it'll come back and everything's cool. And now we can go in here and we can start working with our presets. So you see how the black's expanded. I find that when I'm working with colors that are going to become data for me, I find it's much better to turn off the color correction here, because now what I'm getting is I'm getting black where it's black and white when it's white, and it's not adjusting it to a gamma curve, which is, you know, there's no problem adjusting it to a gamma curve. That's wonderful for when you're rendering and things, but we're not rendering. We're actually using these colors as a stand-in for our data, and that is something that we really need to get a true idea of what's white, what's black, etc, 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 rather than what appears white and what appears black when rendered or on a screen, or all of that good stuff. We're not rendering today. We're not rendering artists today or shading artists today. I don't know what we are. We're procedural artists today. So here is a reasonably good looking Worley noise. Reasonably. It's a good start. There are some things we need to do to it. First thing we can do is very happily, if we want to, we can play with our F-curves, so we can make it darker like that, so it doesn't get to the whites too quickly. We can make it have much less black at the bottom, so it just the very lowest ones are black. That kind of thing. I like to just keep it on the preset, so the smooth, which is, you know, pretty good. It's time to translate it into actual noise now and plug it into our system. So let's get on to doing that. Remember, we are inside a compound, and what we need to come out of this compound is this. So these are the noise values coming out, and using this we can plug this into our amplitude and just scale this independent of everything. So this is what our actual output is our remapped array. Except it's not remapped to the right thing. You remember when we started setting up this, that our mandate was that whatever comes out of the noise needs to be from -0.5 to 0.5. I could have made it 0 to 1. It would have worked. But that's going to screw with our colors. So we actually don't need any of this anymore. We don't need to look at it anymore, because we have our noise, we have our range set up, we have our output. If I remember rightly, I probably don't even need to set up the range, because we've already got one here that does it for us, -1 to 1. Oh, I was wrong. I thought it was -0.5 to 5. It shows you how long it's been since I've done it. So we don't need this at all. We can actually go straight out from the length. That is the most basic of Worley noises. Now it's time to plug it in and see if it works. Let's plug it in. And why are we not seeing anything? I think I've disconnected that output for now. I've turned off the terminal. So let's turn on the terminal. There you go. That is what Worley noise looks like. That is doing what it is supposed to do. We don't have any of our nice sort of curve control or anything in there. We can put that back in. In fact, we very much will put that back in, because that is ugly. So let's just do an eval F curve in here. It's completely up to you if you want to expose this as a control. At this point in time, I'm not going to, because I'm planning for our noise node to have a control as per. Now you see we've run into our problem again, in that what's coming out of here is 0.002 to 3.4, I think. So at this point we would need to remap it if we wanted to run and evaluate. It might be better to evaluate up at the top, but let's do it here. Why not? So we'll change our curve, instead of doing a remap, I can just change the settings in here. I roughly know what's coming out of here, except that these guys are going to change. They're going to change it's going to change in terms of, if I put a different object into here, then these distances aren't going to be the same. So I can't just put into the F curve, I can't just put 0.002 in here and 3.473 in here, because that only works for this. This is procedural. Remember, this has got to be able to change with its inputs. So I'm going to put the set range back in, basically. So I'll put the set range back in. Again, we can expose these controls if we want to. And I'm just going to take it to 0 to 1, which is what the F curve is. You can see it's immediately smoothed out. We had the little dimples in the center, but it's immediately smoothed all of that out. And the reason it's looking kind of chunky at the moment, I think, is because our amplitude is up above 1. If we turn that down to 1, here's all our controls that I've got over in a different window. We can use these to see if everything works. Right now the seed isn't hooked up. We need to hook that up. Now, element size, frequency, and phase aren't going to work because we didn't use them. Amplitude is going to work because our output is coming out of here and being multiplied by our amplitude. So now all of our phase, etc., is still going to be going into here, but if you look into this output here, we're not actually using it. We're using the geometry itself. So this is the first thing we need to look at and think about doing, is how do we, this is the system for making cellular noise, making Worley, I almost said Warrenoy, Worley noise, and it works. It's doing it. It's generating feature points, it's getting the right indices, it's getting the distances in a Euclidean way. We'll work on the other kind of distances as per Houdini later. It's giving us the ability to control that and output it in a certain range. But what it's not giving us is a frequency and an offset. We have a frequency for the Worley noise, that's covered. And that frequency for the Worley noise is this here, this amount in the scatter. If I just pop this out of the way. So if I change this to 30, you can see how that's working. I'm going to need to maybe push the amplitude up a bit to get, goodness me, that's nice and fast, isn't it? To get the right kind of noise out of it. But it's working. So there's a couple of things I'll do very much first, just because they're the low-hanging fruit, and we'll hook it up. First thing I'm going to need is a seed, and I need a seed that goes in here. So I need to make this scatter on object node, I need to make it editable so I can add things to it. I'm going to take the seed and expose that. So when we do this, this is exactly the same as promote attribute in Houdini. It's just not promoting it between points and primitives or points and vertexes, it's promoting it back up the chain. So this is now promoted into here. So I now have a seed object, which can go straight back out into my input, like this, and then we have a master seed over here, which we can now hook up to the seed, and it changes. And I've managed to close the thing I was working on, so let's get this back, copy that tab, and then close that again because of real estate, extra attributes, close that down. So now if I change the seed, it changes. Nice. So just hooking up one controller has given us this much. Excellent. So I now need to promote the frequency, which is the amount. Well, I will promote that back up to the input. There's absolutely no point plugging in this frequency or this size into this because they just don't work the same way. So for example, the element size right now is 0.9. The frequency that we're using in here is 30. If I change that to 0.9, you'd be lucky if there was one feature point. It looks like there is because the sphere is elongated a little bit in one place. So there's really no point hooking up this element size to this amount. It's much, much better to actually make a new control because Worley is a special case. Cellular noise is a special case. So this is our frequency. 90 gives us 90 points. That is a frequency of points. Everybody's happy. Well, not everybody, but those of you that are trying to get a Worley noise working should be reasonably happy at this. And we can push this all the way up to back up to 6,000. It'll take a while to calculate. Quite a while to calculate because 6,000 is a big number, but it will do it. Or it'll crash. One or the other. No, it did it. That is a 6,000 point Worley noise on this object. That's pretty cool. I'm going to take it back down to 20 just because, you know. So let's keep going with the testing. What I'm going to do now is I'm going to switch the object that it's going into and see if it works on all objects. So let's go back to our horse. It looks kind of cool, but it's working. That's one weird looking horse, but it's a horse. How about a plane? That's important. There we are. The plane looks lovely. That's what Worley noise looks like on a plane. So that's working. And then we've got a different kind of sphere in the last one, and that's also working. So we've achieved Worley noise. What do we need to do now to make this work? Well, there's a bunch of stuff we need to do to make this work, and chief among what we need to do, I'm going to go back in here and I'm going to turn that on. This is going to show us the points that correspond to the Worley. One of the things we really need to do to these points is make them a little more evenly spaced, because right now you can see there's no point here, and there's this huge weird looking bulge. Now if you like huge weird bulges, that's wow, whatever floats your boat. But if you don't, the way to fix it is to distribute these points more evenly, and there's a couple of ways we can do that. There's a fast way, and there's a slow way, and there's a custom way, and yeah, there's just a bunch of ways to do it. So what I can do is I can change this, and I can use Bifrost scatter tools, right? So this is the proper scatter points. It wants a geometry. Well, we've got that. That's cool. And I'll just move this up here. And I want some scatter settings. So it wants an amount. Well, we've got an amount. That's our Worley frequency. We'll pop that in there too. It doesn't like that for some reason, but we'll get on to that in a minute. What's the error? No promotion exists. So there's this Worley frequency is a double for some bizarre and interesting reason. Set port type to float. That worked. And it wants a seed. Luckily we have that too. See, it's doing weird stuff over here right now. I'm not entirely sure why, because I haven't hooked this up to anything right now. Oh, because we changed the way the frequency works. Okay. And it reset itself. There we go. We're back. It's fine. So now, positions is what we've got coming out into this pass. So let's put that out and see what happens. Yep, there we go. We've just got, it hasn't done anything yet. It's still a nice random distribution by number. And the amount is our Worley frequency, and the seed is the seed. We have a max number. We have all of this stuff that I haven't provided with my little basic scatter on object. What I'm really looking for here though is blue noise. So we can go to blue noise, and that, why don't we hook up the points as well so we get a much better idea. You get out of there, stop it. Yes, I know, poor thing. There we go. So what blue noise is doing is it's distributing the points as evenly as it can. Yeah, which is great. Yeah, we can change our overlapping radius. We can do all kinds of stuff. This will color overlapping points. So if I change this back to random, where we will get some overlapping points in a radius, this is back to our points. Let's try and find a couple that are really close. Those two are pretty close. Got any closer ones? Maybe. These two it'll have to be. So if I turn on color overlapping and then push this radius up, there you go, see? So it's actually, that's another way to do it. Doesn't help us with our large bulges here. but blue noise does. So this would be something that we could totally add to our Worley system. We could bring this out as a control here. One of the other ways to do it is to build our own relax points nodes, which is how I did it the first time, because when I did it the first time the scatter tools weren't quite released, and that worked. But I'm just going to use this system in here. We don't need our own scatter on object anymore. I'm going to use this system in our Worley noise because I've just taken you through something fairly complex, which involved a lot of loops and some distances. And I don't really want to make this a tutorial about relaxing points, which, you know, there is one coming. It's going to be a Frostini. Keep an eye out for it. And if enough people ring me up and tell me that they want to see how to relax noise without using blue noise, then I'll quite happily go back and include it in this. But for now, I'm just going to use blue noise. So you've just got more control with these, including property transfer. You can set your orientations, you can do stuff in here. We're not really interested in this at the moment. We're interested in this, so I can turn that off too. So it's not culling any overlaps anymore. But our system of generating the Worley noise, which pretty much starts here and goes onwards, is still working. All right, so that's a very basic Worley. We're going to add to this in the next episode. And what we're going to add to this is the ability to do Manhattan distance, Chebyshев distance, if that's how you say it. My Russian is terrible, or rather it doesn't exist. So right now we're doing a Euclidean distance, which is what this is. There's another at least two ways to do distances, and we're basing this on how Houdini does it. So that's all good. But we have a Worley noise. We have a cellular noise now. In the next noise episode, we're going to talk about using that. We're going to talk about the different distances, like I just said. We're going to talk about working on the distributions. We're also going to talk about creating Worley F2 and Worley Alligator, and also what happens when you go in here. Remember I said that we were going to do something else in here with this index, this get from array. Let's do that now, just to see this before we clock off. So right now it's searching for the first one, the closest point. What happens if I search for the second closest point? You get a different pattern. It's a different kind of noise, and it's still pretty cool. What about the third closest? So we're getting some pretty nice facets and stuff like that. So something to bear in mind for later. All right, so really quickly what we did is we made a new noise, a Worley noise, calling it Proto Worley for now because we haven't finalized it. We generated a set of feature points originally just by scattering on our object, but for now we're scattering with the scatter tools because they're better. We then went through every single geopoint, and inside the loop with every single geopoint, we went through every single feature point. And inside that loop, we got the distance from the geopoint we were working on to the feature point we were working on. Then we got a distance array. We sorted that from smallest to largest, the smallest being the closest. We got the closest index. From our sorted array, we got the lowest distance point. We then found that in our distance array here, which gives us the index of the closest feature point to every geopoint. We then got those from the feature points. We subtracted them from the geopoints, and we got our distance. We then used that distance to displace the points in our object, and that is how we make cellular noise. That's the basis of it. What's coming up is, like I keep saying, there's a bit coming up, but one of the big things that's coming up is the ability to change the frequency, the amplitude, and the phase of this. Spoiler alert, you can already change the amplitude, and you can change the amplitude because we set up our amplitude to be outside. Now, if I change the frequency, nothing's going to happen. This connection here doesn't do anything. Worley wants it for some bizarre reason, but it's not actually hooked up to anything, so that's still going to work. So we don't actually have this information coming in, which is where we're doing our multiplier, we're doing our frequency, our element size, and all of that kind of thing. None of that is coming in. We need to find a way to tie this to that, and we'll do that in the next episode. But there we go, cellular noise. It's our first custom noise, our first real custom noise. Don't even get me started on sparse convolution. That's going to take some research. Hope this has helped and you understand it. Any questions, just leave them under the video, or you probably are getting an idea of where to find me by now. Thanks for listening, and I'll see you next time.